Okay, okay. No, recording will take a little time. Huh? Let the speaker join. Huh?
Good evening, sir.
Yes, sir. Good evening.
Yeah.
Good evening, Professor.
Am I audible?
Yes.
Yes, yes. Yeah.
PVS, can you just stop your presenting so that Dr. Aswani Kumar can present his slides?
Sure, sir. Good evening, Dr. Aswani Kumar. Just stop.
Good evening, sir.
Yes, sir. Good evening, Professor.
Am I audible?
Yes.
Yes, yes. Yeah. Sir, are you able to see my screen? Slides?
Yeah, screen, but can you do the present slides? Can you start the slides?
Yeah, yeah.
Okay. Yeah. Yeah, slideshow, please. Okay. Yeah. Fine. We're able to see the slide.
You are able to see in the full screen, no, sir?
Yes, yes. We are able to see the first slide.
Yeah.
Okay. Akila, can we? Yeah. Fine. Akila, can we start recording? Okay. Just as soon as the recording starts, we can initiate. PVS.
Yes, sir.
Okay, PVS. We can start.
Yes, sir. Good evening, participants. ACM Chennai, IEEE CS Madras, and CSI Chennai cordially invite you to a webinar on Demystifying Quantum Computing Technology by Dr. Aswani Kumar, ACM Distinguished Speaker, Professor, School of Information Technology and Engineering, Vellore Institute of Technology, Vellore. Conventional computing at the saturation levels in terms of achieving more computational capability. Further, there are several computational problems that are hard to be solved by conventional computers. Quantum computing technology provides an exponentially larger computational space and power derived from quantum mechanics principles such as superposition, entanglement, interference, and coherence. With these principles, quantum computing provides radically different solutions to the computational problems and even solve problems that are not tractable to the conventional computers. Due to these reasons, research in quantum computing is fascinating, curious minds of researchers in several disciplines. This lecture provides a detailed understanding on quantum computing, building blocks of quantum computers, properties, implications, and applications of quantum computing technology. Further, it provides insights into various conditions and challenges in developing large-scale quantum computing systems that can solve practical problems. Also, this lecture discusses the limitations and open problems of the technology. I will introduce the speaker now. Dr. Aswani Kumar is professor at School of Information Technology and Engineering, Vellore Institute of Technology, Vellore, India. He holds bachelor's and master's degree in computer science from Acharya Nagarjuna University, India, a PhD degree in computer science from Vellore Institute of Technology, India. His research interests are information security, machine learning, and quantum computing. He was a recipient of Young Scientist Fellowship from Tamil Nadu State Council for Science and Technology. He was a recipient of the Indian Express Inspiring Teacher Award 40 under 40. He has executed few research projects funded by the Department of Science and Technology, Government of India, Department of Atomic Energy, Government of India, Ministry of Human Resources Development, Government of India. He published more than 100 refereed research articles so far in various national and international journals and conferences. He has delivered technical talks at several national and international conferences. He is the editorial board member for several international journals. He is a senior member of ACM. He has organized a 3-week summer school on information and system security in association with ACM India during May and June 2017, which attracted students from across the country. Over to Dr. Aswani Kumar. Thank you.
Thank you very much, sir.
The slides are missing, huh? Someone has started presenting. Slides are missing. Annapurna is presenting, looks like.
No, it is. I'm sorry about that, sir. Actually, I'm using my wife's laptop because there is.
Okay.
As I've mentioned, when we are checking this from the, I will be presenting from my other laptop.
Okay. Fine.
Are you able to see my slides, no, sir?
No, not visible.
Right.
I think you can. It's not visible. Slides are not visible.
Hello.
Yes.
Sir, are you able to see my slides or not?
No, not able to see.
Oh, again
I think you can re-log in.
No.
Yes. Okay.
So,
fine.
I would like to sincerely thank the organizers, Professor H.R. Mohan and others, for inviting me to deliver the a webinar on quantum computing. And this talk is made through the ACM Distinguished Speakers Program. And all of you are aware about the ACM. It's a professional body which is known throughout the globe, and it has about both computing professionals and students across the globe, with spanning across 170 countries. And the mission of the ACM is to help the computing professionals to be their best and most creative in their profession, and we connect them to their peers, to what the latest developments, and inspire them to advance the profession and make a positive impact on the society. That is the mission of ACM. And the vision of ACM is we see the world where computing helps to solve the tomorrow's problems, where we use our knowledge and skills to advance the computing profession and make a positive social impact throughout the world. And I'm glad and proud to be an ACM member for the past 13 years or so. And present, I'm the senior member of ACM. And this particular talk is made possible through the Distinguished Speakers Program of ACM. My talk of the day would be covering about some of the fundamentals of quantum computing. And when I looked at the participants' details, I was amazed to see that the talk has attracted more than 500 the audience, and majority of them are students spanning across different disciplines of engineering and science and technology, and from throughout the country. And there are working professionals and the other senior faculty members of various institutes. So I would be covering more aspects of fundamentals of the quantum computing and its principles and how it has evolved, and the fundamental building blocks of quantum computing in the sense and the quantum gates, and what are the various types of quantum computers, and the applications of the quantum computing, and the current trends that are happening in the industry, and where is the current research in terms of quantum computing. And these are the topics that I would be covering throughout my session. And of course, the topic is evolving. And in fact, now, as when computer science started evolving in 1950s and all, how the computer science has grabbed the contributions of mathematicians, physicians, and electrical engineers, electronics. So in the similar manner, the quantum computing now is attracting contributions from various other disciplines, in the way that it is going to make a positive impact on all other disciplines, starting from drug discovery, the chemistry, the mathematics, and trying to solve some of the problems that the classical computer, is failed to solve. So, and also there are certain myths about quantum computers that it would be replacing the classical computers, but it is not so, which that point also I would be touching upon in my slides that are going to come. So let us proceed. As Seth Lloyd, who has contributed significantly towards the quantum computing, has given a quote saying that classical computing is like a solo voice, where one line of pure tones succeeding with each other, whereas the quantum computation is like a symphony, where many lines of tones are interfering with one another. So it's a beautiful analogy that Seth Lloyd has given about the quantum computing. When we move further, we can correlate that with how the qubits are going to work together in a superposition, exploiting the superposition principles and entanglement principles. We can correlate this with the analogy that what Dr. Seth Lloyd has mentioned. Also, I want to connect the quantum computing principles with the Hindu mythology, where we have a verse that says, Vagrata vivasamto vagrata pratipattaye Jagathat Pitaro Vande Parvati Parameswaro, wherein which we pray the parents of the world, Lord Shiva and Goddess Parvati, who are inseparable in the sense, we have Ardhanarishwara as one of the icon of inseparable nature of both Lord Shiva and Mother Parvati. And they are inseparable in the sense that as speech and its meaning, they are linked together. In the same manner, when we proceed further, we can give this analogy and attribute it to the quantum computing principles, wherein which two qubits are entangled with each other, and state of one qubit affecting the state of other qubit. Like this, we can bring analogy to our mythology and to our real world principles, real world applications, and try to understand this somewhat complex topic, but we can simplify it and try to understand it in a better manner. And we observe the evolution. If you observe the technology, and if you observe the civilization and the way the things have moved from starting from the formation of universe about 13.5 billion years ago, we have a Big Bang theory, and then we believe that the formation of the universe is through that particular Big Bang theory. Then onwards, we have a beautiful subject of physics, wherein which matter and energy started to coalesce into a complex structures called atoms, and that has given the birth of the subject called physics. And when the atoms are started to interact with each other, and molecules started forming, we have a subject called chemistry. And about 3 billion years ago, on this planet Earth, we have certain molecules that are combining to form an organism, and that has given a birth to the subject called biology. And the Homo sapiens started about 70,000 years ago, and hence we have civilization, and then history has started. And then when these Homo sapiens, the brains of the Homo sapiens got getting maturity, about cognitive revolution started about 70,000 years ago. And we have agriculture revolution about 12,000 years ago. But whereas the scientific revolution started about 500 years ago. And in that, if we observe the computer science, it's almost about not even 100 years ago. But in the last, the 80 to 90 years of span, how computer science has evolved, how computer science has emerged, and then how it has impacted the other branches, and it has impacted positively our lives is tremendous. And in that, if we observe the computer science, the core, the present computers, what we are using, we all know that it's based upon one human computer architecture, and it has beautifully served the purpose of solving several problems: scientific, technological, business, financial, several problems. And the algorithms, the hardware, the software aspects were able to beautifully build in the last 80 to 90 years, and the networks that have emerged. But then we all know that there are certain problems that this human architecture is unable to solve, and then people started looking at scaling up the processing power that is available, and looking for the other alternate architectures, whether if any kind of new architectures that can emerge and then solve the problems that the human architecture is unable to address. So that's how the people started looking at the quantum computing. As we all know, though we have enormous amount of processing power, we have certain exponential growth problems in classical computer science, and there are certain problems that are not tractable to the classical computers. One typical example, the way when we scale up the problem, the complexity gets increased. One of the typical example is we have a problem wherein which you have to keep a food grain on every starting from first block to the last block of the chess. If you start keeping one food grain and doubling it for every block, and the number of food grains that would be required when we reach to the final block of the chess, that would be requiring about more than 18 quintillion food grains, which would be leading to around 1 trillion metric tons of the grains. That's an enormous amount of food grains. If you can model that particular number of grains problem, the number of grains that are required on any square of the chess, that reflects through this particular formula where n is equal to 2 power k minus 1, where in which k is the number of square in which on the chessboard, and n is the number of grains that are required on that particular square. So if say we are at the first square, k is equal to 1, and obviously we need 1 food grain, and so on. If we proceed further, we can notice that there is an exponential growth because of that exponent or the power that increases as we grow from one square to the other square. And also the number of calculations. Of course, when we move from the way computer science has the computers have emerged, the number of calculations that we are able to achieve per second per $1,000, it has moved up, and through that, by now we have reached to a scale of mimicking one mouse brain, but we have a long way to go to achieve the ability of one human brain. Probably people expect that we will be reaching around say 2030 or so. And imagine if we have to achieve the computationals that all human brains on the particular on this planet Earth, if they to achieve, probably we may have to go another 30 to 40 years. So there is a need for increasing and acquiring the computing power. So in the beginning, when we look at the way the computer science has emerged, and I think on 30th we are going to have eminent professor Dr. Rajaraman's lecture on the past, present, and the technology of computer science. The way how the things have emerged. So in 1942 we have vacuum tubes, 50s we have silicon transistors, and 1960s we have quad gates, and 1970s we have 8-bit microprocessors, and 80s we have 32-bit microprocessors that contains about 275,000 transistors, and we have GPUs now. So in the sense that the earlier technology of computers was depending on the technology that was available on those days, especially the vacuum tubes, and then transistors, and finally the ICs. Okay, and in fact, these technology that was matured enough on those days to support those applications, especially the radio, television, telephony, okay, which were the driving commercial applications of those days. Okay, in the similar manner, the current also we have the Moore's law that says that transistors density on an IC doubles about every 2 years. That means performance of the modern computer systems doubles, which means increases about 1,000 times for every 11 years. Okay. So although Moore's law reflects a great progress in classical computing over several decades, it is clear that this exponential trend cannot be sustained because of the limitations in the physical limitations and the finite size that is of the world market. So at this particular backdrop, only the quantum computing, people started looking at quantum computing as an alternate the paradigm that can solve some of the problems that the classical computer cannot solve. And there is a estimation by a set of researchers from Russia talking about the limitations of the von Neumann architecture, and they have given a beautiful analogy or estimation about on different application segments, say security, aerospace, and mechanical engineering, especially automobile, aircraft, shipbuilding, nuclear engineering, oil, gas, and industry. What would be the petaflops or exaflops of the the computationals that are required starting, they estimated about in 2018 what would be the case, and 2022 what would be the case, and 2025 what could be the requirement from these particular several disciplines or several application areas. So, and these are the computations that are required in order to address the problems of those disciplines, and also to achieve accuracy and correctness in addressing those problems. So the classical computing devices increased the computing performance by many orders of magnitude by making the either two ways. One, by making the operations faster, that means increasing the clock frequency, or on another hand, increasing the number of operations completed during each cycle. 1993, Brinstein et al. Have showed that the quantum computers could violate the classical Turing thesis, and in 1994, Peter Shor had showed that a practical example of finding, finding the prime factors of a large number, which is one of the significant breakthrough in developing the quantum computers. In fact, that is one way is helping the quantum computing to proceed further, and at the same time that is giving a threat to the current security mechanisms that are essentially built upon public key cryptography, and which fundamentally uses this particular problem of not able to finding the the prime factors, which is the security of the algorithm. And if this particular issue is solved, I think that would be a big threat to the security algorithms as such. But at that time of the 93 and 94, there was no maturity in the technology per se, in the sense that how to build a quantum computer, or else even the fundamental building blocks of the quantum computer, like say qubit, how to build. So that was people were not able to proceed. But these results, especially the Shor algorithm, of course, there is another algorithm called Grover's algorithm. These results have catalyzed the interest among the researchers in developing other quantum algorithms, exponentially with exponentially better performance than the classical algorithms, and trying to create basic quantum building blocks from which quantum computers could be built. So on the other one side, we have the software that is getting maturity, and on the other side, the hardware also. In the last 15 to 20 years, we have the maturity of this to some extent. So, in the sense that this maturity or the progress of the last 15 to 20 years, we can even correlate that analogous to the growth that has been achieved in the performance of the classical computer. We can see the correlation between both. So the quantum computing harnesses, especially the quantum mechanical phenomena, to greatly to enhance the way in which a couple of things. One, the way the information is stored, represented. First of all, information is represented, information is stored, and as well as information is processed. So in these three dimensions: one, representation; two, storing; three, processing. In these three dimensions, quantum computing has is greatly depending on the quantum mechanical phenomena. And but as I've mentioned, the physicists and mathematicians were able to propose several theories, but the scientists and engineers, they could be able to build the computers in the last 5 to 6 years down timeline. The last 5 years, we have seen the hardware capability and software capability moving from the university lab to the industry giants. A lot of startup have come, and similarly the technical the industries such as IBM, Google, and they are also heavily investing on this particular the quantum computing. So in classical computer, the basic unit of information is a bit. We all know that we have the 0 or 1. In the case of quantum computer, the basic unit of information is, we call it as a qubit. So a bit in a classical computer, in a quantum computer, it is qubit. So through quantum mechanical phenomena such as the superposition, entanglement, interference, coherence, these are the various quantum mechanical phenomena or quantum principles on which these qubits perform several computations simultaneously and providing an exponential computing ability to the quantum computers. So that is making the quantum computers to solve certain problems which are difficult and that classical computers are unable to solve. So the current classical computing machines, they follow the classical laws of physics in representing and processing the the information. And these classical descriptions follow the Newtonian physics, provide an intuitive and deterministic explanation of the physical universe, but they are failed to predict all observable phenomena. So this realization has made in the 20th century to follow the quantum physics phenomena, which are actually not deterministic, in the sense that the quantum computing results, when we move further, we observe that the results of the quantum computing would not be like a deterministic like a typical classical computer. They would be like a probabilistic, and hence they have inherent uncertainty. So the quantum mechanics and quantum physics are the backbones of the quantum computing. So according to the theory, the quantum object does not generally exist completely in a determinate and knowable state. That's what I have mentioned about having uncertainty or the probability nature of quantum computing. Each time when we observe a quantum object, it looks like a particle, but when it is not being measured, it behaves like a wave. So this is the principle which people call it as wave-particle duality, and which is leading to many interesting physical phenomena. So before we proceed further, there are many hyped statements being made about the capabilities of quantum computing, that it would break modern encryption methods in seconds and solve several intractable problems in minutes, and also it may replace the classical computer like that. There are several statements, but there are certain things which theory it is possible, like breaking the modern encryption systems, but in reality the quantum computers, I think there is a lot of time or maturity that need to be achieved to that stage. Also, it is unlikely that classical computing will be replaced by the quantum computing. There is also a very much hyped statement. So the more likely future scenario is that the quantum computing will augment certain subroutines of the classical computers. So we can see a hybrid interplay between classical and as well as quantum computers, even in several applications such as optimization problems and all that. So problems that cannot be solved on the classical computers but can potentially be solved on the quantum computers are the ones that are going to be worth in the near time. So these are the various milestones of the quantum computing. In 1992, David Deutsch, in fact, is regarded as a father of the quantum computing. They gave the idea of having the quantum computers, and predominantly the two algorithms. One is the Shor algorithm, wherein which people were, Professor Shor has shown that the quantum computers can factorize the large prime numbers and large numbers and identify the prime factors. So that is one of the algorithms that has the potential to break the RSA or public key crypto system. And similarly, the Grover's algorithm, which is used for search problems, especially the unstructured problems, that has given a big push in the sense that worst case complexity of finding executing a query with n was reduced down to root of n. So that is the square root speed up given by the Grover's algorithm in the unstructured database search. These are terms that have created the big impact on the quantum computing domain. So before we proceed further, let us understand some of the interesting or fundamental principles behind the quantum computing. One, we said about the backbone of the quantum computing is the qubit, wherein which a bit can be either in a 0 or 1 state, whereas a qubit can represent values either 0 or 1 or both. So it is like that. So a bit, we all know that either it represents 0 or 1, whereas a qubit can represent the values either 0 or 1 or both, combination of both at the same time. This is the fundamental principle called as superposition, on which the quantum computing is based upon. So the state of classical computer is determined by the binary values of collection of bits at any single point of time. The state of quantum computer with the same number of quantum bits can span across all possible states. So that is the ability of the quantum computer achieved through the principle of superposition. However, the ability to make use of such a big, huge span, in the sense that to utilize all the quantum states or all the qubit states, it is possible only when these qubits are connected together. This connection of qubits together is called as entanglement. And these qubits should be isolated from the outside environment and should be precisely controlled. In fact, that is the one of the bottleneck, or that is the one of the major of the constraint now in building a real-time quantum computers. What as of now we have is nice intermediate state NISQ quantum computers, because they are having still noise aspect is not yet minimized or controlled. So we know now what is a qubit. Qubit is a fundamental building block of quantum computer, and in the classical bits, classical computer we call it as bit. In quantum computing we have a qubit, and this qubit would represent the values like classical, in the sense it can represent 0 or 1. But in addition to the classical like 0 or 1, it also represents a combination of both states, in the sense both as 0 and 1. So how it represents that we will see in the upcoming slides. So that combination position or combination state is called as a superposition state. And these combination positions of one qubit and similarly with multiple qubits can connect intrinsically each other, which we create as an entangled state. So quantum objects can exist in multiple states all at once, with each of the states adding together and interfering like waves. So, which in fact they utilize or they exploit the property of the wave particle duality. So, as long as we do not measure it, they are like in a form of a wave. As and when we measure it, they become like a particle. So, in general, the state of any quantum system is described in terms of a wave functions. So we'll see what is a wave function, and for when we proceed further. Similarly, the state of a system can be expressed generally through a mathematical term as sum of all the possible contributing state, each scaled by a complex number coefficient that reflects the relative weight of the state. This is another fundamental principle in which a wave function of a qubit is represented as a sum of all possible contributing state. For each state, again, there would be a weight, and that weight would be represented through a complex number. So a wave function that we will be checking it in the upcoming slide. Similarly, the states are said to be coherent because the contributing states can interfere with each other constructively and destructively, much like a wave fronts. As I've mentioned, when they are entangled, one state of the qubit would affect the other state of the other qubit. So the states are said to be coherent because the contributing states can interfere with each other. So when we attempt to observe the quantum system, like in a wave, when we try to observe, only one of its component is observed with the probability proportional to the square of absolute value of its coefficient, which is typically represented in the form of the complex number. So to an observer, the system will always look like a classical when measured, but when it is not measured, it is in that superposition and entanglement state. So observation of a quantum object, we call it as a measurement. So that occurs when the object interacts with some larger physical system that extracts information from it. So when we measure the quantum state of a qubit, it becomes into a classical output. But again, when I say classical output, it's not a deterministic output, it would be a probabilistic output. So measurements fundamentally disrupt the quantum state, and it collapses to a measurement state that is the single observable state. After the measurement, the quantum object's wave function is that of the state that was detected rather than that of the pre-measurement state. That also, all these are the theoretical concepts that we will be checking it when we proceed it further with the qubits and the wave functions and the qubits representations and all. So far, I will just summarize. We understood what is quantum computer and what it will do, and what principles it is based upon, and what is the building block of the quantum computer is a qubit. And we understood, or we have learned about some of the fundamental principles like superposition, entanglement, and the measurement, and the interference and coherence. So there are a lot of examples in the literature about being state to be in a superposition state, like both in on state, off state, how it is possible. So a beautiful analogy is given towards the example of coin toss. As long as that coin is not tossed, it is like in a in its regular state. But when it is tossed, the coin could be either, nobody knows whether it is in the, when it is in the tossed position, nobody knows whether it is in the head or tails. So, but upon collapsing, people knows that what is the probability of having whether it is a head or tail. So, analogy can be given to the coin problem of, and also we can see further about this particular problem in a better manner. So, under some circumstances, two or more quantum objects can be intrinsically linked, such that measurement of one particular quantum object detects the measurement of the other quantum object, which property is called as an entanglement. So, the states of entangled qubits cannot be described independently, but rather, one object describes the other object. In order to control the quantum systems, one must therefore carefully control its energy environment, both by isolating the system from the rest of the universe and by deliberately applying the energy fields within the isolation region to elicit a desired behavior. So this is where the controlling of the qubits is very, very important, and that is one of the major challenge for the scientists and engineers to get the desired outcomes from the quantum computer. In practice, complete isolation, as all of us know, is not possible. Although interactions with the environment can be minimized, the quantum system will ultimately exchange some kind of energy and information with a broader over time, and that process is called a decoherence. This can be thought of as an environment continuously making small random measures on the system, each of which cause a partial collapse of the wave function. And when we, still scientists are trying to address, these are the issues. So quantum computer in general is defined as a physical system that comprises a collection of coupled qubits that may be controlled and manipulated in order to implement an algorithm such that measurement of the system's final state yields the answer to the problem with a high amount of probability. As I've mentioned, it's not a deterministic answer. So let us see how the information is represented in classical computer and as well as in the qubits. So in classical computer, all of us are aware that a computer runs on bits that have the values either 0 or 1. Quantum bits or qubits are similar in that for practical purpose we read them as a value 0 or 1, but they can also hold much more complex information and even negative values. So before we read their value, they are like in an intermediate state called a superposition state and can be influenced by other qubits also, like an entanglement. So this particular diagram that gives you a better understanding of the classical computer, similarly the quantum qubits. The classical bits, the 0 or 1 only possible. So the discrete number of possible states 0 or 1, and they are deterministic, and the repeated computations on the same input will lead to the same output. This is another fundamental difference that what we can derive between the classical and quantum. When you repeat the same computation with the same input, since the quantum outputs are probabilistic in nature, you cannot guarantee the same output. So there are infinite number of possible states, unlike a discrete number of possible states in the classical. The quantum, there are continuous number of possible states, and the output is probabilistic. Measurements on the superposed states yield probabilistic answers. So it is not like a deterministic in the case of classical. And how the information is processed in the classical computer, at the fundamental level, bits are processed sequentially, as we all know, which is similar to the way a person would solve the problem in a step by step. That's how the algorithms would proceed. Whereas in the quantum computation, superposition qubits are entangled together, so that changing the state of one qubit influences the state of other, regardless of whether one qubit and both the qubits are in the same place or whether they are separated at the physical distance. So this allows the quantum computers to intrinsically converge on the right answers to a problem very quickly because they are in the superposition state. How to interpret the result, that is another fundamental understanding, is that classical computer, we all know that only the specifically defined results are available and deterministic. Whereas in the quantum, the answers are probabilistic, meaning that because of the superposition and entanglement, you have multiple possible answers are considered for a given computation. So what people do, they repeat the experiment and then see what is the answers that are getting converged. So problems are run multiple times, giving a sample of possible answers and increasing the confidence in the best answer provided. So you need to have some kind of a likelihood ratios and all that. These factors allow quantum computers to solve certain classes of complex problems much more efficiently than classical computers, especially the qubits nature of being in a superposition state and entanglement states. So classical computers would take more and more time for each of the variable added. Quantum computers can harness the properties such as entanglement, the superposition to solve the complex problems. So this is the a table that gives you the illustration of comparison between the classical computers, especially classical supercomputers that are presently available, and the quantum computers, the way in which the information is stored. We all know that it is in bits, whereas here it is qubits. The way information is processed is through the classical logic gates such as AND gate, NOT gate, and all that. Similarly, in the case of quantum, we have logic gates. Of course, there are other ways of implementing the quantum computer through, the quantum annealers and all. But typically, logic gates are the one people are now trying to push to a greater extent. And the classical computers circuit behaviors are governed by the classical physics, whereas the quantum computers are typically governed by the quantum mechanic principles. The representation of information is through the binary digits, whereas in the case of here, the qubits coupled with the classic, the quantum principles such as superposition and entanglement and all that. So here, the mathematical principles are purely depends upon the Boolean algebra principles, whereas in the case of quantum computing, they are heavily dependent on the linear algebra over the Hilbert space. And there are certain advantages of classical computers, but similarly, there are advantages for the quantum computers in the sense that they are faster and they can tackle the certain subclasses of the problems that conventional computers cannot solve. In the case of disadvantages, if you observe, there are several restrictions about the quantum computers as well, especially restrictions over the measuring, copying the signals, because you cannot copy the quantum states. And that is in fact giving a better edge in designing the quantum key distribution and quantum powered security. And there are a lot of noise and other issues that are there in the case of quantum computing. So this particular table gives a better understanding of the differences between classical and quantum computers. So we look now at the qubits, especially the wave functions. So we said so far that the quantum bit or qubit has every quantum bit or qubit has two quantum states. The qubit can be in either the state. It can also exhibit the superpositions of the two. That means it can be in the state of 0, it can be state of 1, or also it can be state of both. How to represent this and then move forward is through the notation called Dirac notation, wherein which state labels are represented through bra and ket notations. So a qubit's two components basis states are generally written as 0 and 1, and any given qubit function is a linear combination of these two states, that is 0 and 1. So we write that wave function as psi as a0 0 plus a1 and 1, whereas this a0 and a1 are the complex numbers which are actually the coefficients for the basis states 0 and 1. And this is how we write the wave function of a qubit. So as we have talked about the classical bit, you have only the either 0 or 1. So the possibilities for having the classical the output for the possibilities for the classical bit is 1 out of 2 power n possible permutations. Whereas in the case of quantum bit, if you have a qubit, we have 0 or 1 or both 0 and 1, and hence we have all 2 power n possible permutations are possible from the quantum bit. This is what is the fundamental difference and giving the enormous power to the quantum bits be available in all possible permutations of 2 power n. Whereas in the case of classical, at any given point of time, you have only 1 out of 2 power n. But in a superposition state, the quantum bit could be in all 2 power n possible permutations. So we write the qubit as a wave function, as I've already mentioned. So the mod a naught square corresponds to the probability of detecting the state 0, and a1 square to the probability of detecting the state 1. So the sum of the probabilities of each possible output state must be 1, which is the fundamental condition. And classical, while a classical bit is entirely specified as either 1 or 0, qubit is specified by the continuous values of a0 and a1, and this is a kind of analog in nature. That means if we observe closely, while the classical computer is trying to remove the analog nature of the analog nature or analog principles, the quantum is bringing the analog nature or analog principles. So now let us see how we measure the outcomes and probabilities for a single qubit. Imagine we have a single qubit, and we discussed that the single qubit can be in the position of in a state of 0 and in a state of 1, could be in the superposition state of both 0 and 1. And we said when we measure the qubit, the outcome would be probabilistic in nature. And we also said that we can represent that qubit in the form of a wave function. So these are the things what we have discussed so far. Now let us see how we measure and how we measure the outcomes and probabilities for a single qubit first. So let us say we have a qubit, a single qubit, and imagine the pre-measurement state. That means, before measuring the state of the qubit, imagine it is in the basis 0. So state of the qubit is 0, and obviously when we measure it, the measurement outcome would be 0, and probability of getting that 0 is 100%. And post measurement, that means after measuring the qubit, it would be in the same state of 0. Let us take the same qubit, and imagine it is in the before measuring, the state of the qubit is in 1. So during the measurement, obviously it would be in the state of 1, and the probability of getting that outcome is also 100%. And in the post measurement, the state of qubit would be in the state of 1. Now this is the first two cases are like a typical classical computer. Now let us take the superposition state. Now the superposition state is the third case, is the superposition state, wherein which the qubit is represented to the wave function. So psi is equal to 1 by root 2 of 0 and 1 by root 2 of bracket 1. So the point is when we measure it, to get a qubit state of 0 is having a probability of 50%. Similarly, in the measurement outcome to get 1 from this particular qubit, which is in the superposition state of both 0 and 1, is having the 50%, and the post measurement states to get 0 is 50%, and to get the post measurement state 1 is 50%. So 50% probability to get both these states. Now imagine if we change this the coefficient values, or else the weights to get this particular quantum states to a little bit 1 by 2 for 0 state and root 3 by 2 for 1 state, then obviously the probability of having getting 0 after measurement is 25%, and post measurement of that qubit would be 0. If we want to get post measurement qubit state to be 1, then the probability of outcome is 75%, and that depends upon the weights that what we are fixing here for the qubits, or else the complex coefficients that are available here. Similarly, we can define, as I've mentioned, we can define these coefficients to be the complex numbers, and accordingly we can have the probability outcomes varying at different probability numbers. So the result of the measurement looks like just a classical bit when we measure it, with the associated probability of getting each value proportional to the square of the absolute value of the coefficient of the corresponding state. So whatever is that square of the coefficient, that would be the having probabilistic outcome. So upon measurement, the qubit's coefficient or amplitude becomes 1 in that particular state, that is red, and 0 in the other state after the measurement. So for a qubit in a superposition state, the outcome of the measurement, even a known state, cannot be predicted with certainty, as we have seen now. So the superposition state, that what we have seen, the third KSI, has an equal probability of 50% getting the 0 state and as well as 1 state. Now, how we finally come to the outcome is the repeated preparation and measurement of this state will yield a random sequence of outcomes approaching an equal incidence of each as the number of trial increases. So like in the case of a classic and coin flip problem, that what we have just said about a few minutes back. Now let us scale it to single bit to the 2 qubits. Now imagine we have a system of 2 bits, in the sense 2 qubits. Classically, we have 2 bits means, classical 2 bits means they exist in 4 possible configurations. So 0, 0, 0, 1, 1, 0, and 1, 1, and also any one of these possible configurations. In the case of quantum, as we discussed, it is not in one of that, but it is in a superposition of all 4 quantum basis states like 0, 0, 0, 1, 1, 0, and 1, 1. So it is possible for a quantum computer to be in all of these 4 quantum basis states, whereas in the case of classical, it is any one of the 4 possible configurations, which are 0, 0, 0, 1, 1, 0, and 1, 1. So the 2 qubit system now requires 4 complex coefficients or the complex weights. So like A00, A01, A10, and A11 to describe the quantum state. Now I think, though I have not given here the wave function for the 2 qubit state, or you can visualize or you can think of having think of what would be the wave function of a 2 qubit system with complex coefficients and the quantum basis states. So A00 0, 0, and A01 for 0, 1, A10 for 1, 0, and A11 for 1, 1 basic states. So the computation would be executed using a single quantum gate, which we would be discussing after the couple of slides, and that would operate on all possible states. In the sense, in this case, 4 states in parallel at the same time. That is what is the power of the quantum computer. Now let us see the measurement probabilistic outcome of this 2 qubit system. Now imagine if the 2 qubit system is initially in 0, 0 state, and upon measurement, if we have to get 0, 0, and probability of getting the outcome is 100%. So it is like a first 2 cases are like a typical classical cases. Now the superposition state. The third state is the superposition state. So the first state is a 0, 0 state, the state where only A00 is non-zero and remaining all 0. So measuring the first particle yields 0 with 100% probability. And the same with the second particle. So imagine if we want the 0, 1, in this case, each qubit can be described independently by its own wave function. So Wi is the first qubit and Wj is the second qubit. The whole system can be written as a product of individual qubits, which is, when we say product, it's a tensor product. Which is the same as writing 0, 0. Now imagine if it is 0, 1. So this is the tensor product representation of these 2 qubits. So 0, 1 would be represented as 0, 1, 0, 0 through the tensor product between the 2 qubits, the 0 and 1. So typically the bracket notation for the 0, we write it, ket notation for the 0, we write it as 1, 0, and for 1, 0, 1. So the tensor product of it would leads to this particular the state 0, 1 to 0, 1, 0, 0. So this is how we represent or write the whole system. Now imagine if we want to go to the third state, that is the superposition state. So where in which we have only the qubit is with the 2 basis states, that is 0, 0, 1, 1. And hence the complex coefficients are written as 1 by root 2 and 1 by root 2, and the sum of it would lead to, as the condition says, it's 1. So imagine if you want to measure the first qubit. When we measure the first qubit, if we get a 0, obviously we have only 2 states. So if you get a 0, obviously we get a measurement outcome is 0, and having a probability of getting the outcome is 50%. Imagine if it is First, when we measure the first qubit, it has 1, and we have only the next state is the second qubit also as a 1, and hence this would be the outcome, and having to get that is the outcome for the probability of getting that outcome is 50%. And post measurement, the states of the qubits are 0, 0, and 1, 1. Now this is the true so the measurement of one particular quantum state determines the state of the other. This particular condition is called the entanglement, in the sense that we know 0, and then when we have 0 and the qubit, next qubit is also in the 0 state, and we get 50%. And whereas in the case of second, when we have measured the first qubit as 1, and we are getting the we have another state only 1, and we are getting 50%. Now if we look at the fourth equation, we have 4 states, and accordingly we have the probability outcomes for every of all these states, so 25%. So mathematically, entanglement arises when there is no way to write the qubit wave functions as the product of 1 qubit wave functions. Now imagine if we are scaling it up to the 3 qubits. So if we deal with a lot of qubits, it becomes more and more number of states available, and we have more computational power. So to describe a 3 qubit system, we need 2 power 3 8-dimensional space. And more, when we add 1 bit in a traditional computer, the size of the required memory increases only by 1 bit. That is 1 binary cell. When emulating a quantum computer using a traditional one, adding 1 qubit results in doubling the memory in use. So this diagram illustrates addition of qubits and addition of bits in the case of a classical computer. So following this logic, an n-qubit system requires 2 power n coefficients to be specified rather than n bits as in the case of classical computer. This is the richness of the quantum computer, and of course, when we move further, we need n number of complex coefficients. Processing that also would be a tough task. Now, how to realize this the quantum qubits? There are various technology from the different the physics techniques that are available, from the solid state, optical, and nuclear magnetic, and especially now trapped ions is the one which a lot of people are heavily depending on getting the realization of the qubits, to realize the qubits for a quantum computer. Though there are several other ways of representing or realizing the qubits through semiconductors and superconductors like electronic spin and all that. People are heavily depending now on the trapped ions. And several companies, the people, are investing heavily on these technologies, say trapped ions or the annealers. So especially D-Wave company has realized the qubits by now about 2000, between 2000 and 5000 qubits they could realize through the quantum annealer principles, whereas the IBM and Google, they have achieved about 50 to 100 qubits, and they are progressing towards achieving more number of qubits in the down the line. As we discussed, there are 2 types of having the quantum computers, which are adiabatic quantum computer and the gate model of the quantum computer. So these 2 methods are explored using various hardware implementations, and both are having the strengths and weaknesses. Adiabatic quantum computers are typically based upon the annealing principles, and gate-based models are trying to realize quantum gates through that are built upon the qubits. So annealers are least powerful and most restrictive form of quantum computers, and it is a special case of adiabatic computers are the special case of quantum annealers. And the main application area of this particular quantum computers are the optimization problems. And gate-based models, this is somewhat technically challenging to build the gate-based models because they are hardware specific, and gate-based quantum computers perform calculations by manipulating the quantum states via applications of the gates. and these quantum gates form building blocks of quantum circuits in a manner similar to how classical logic gate form the building blocks of conventional digital circuits. There are several quantum gates that are similar to classical gates. The compulsory condition is that the quantum gates must be reversible and they act on qubit instead of a classical bit. And quantum logic gates are represented by unitary matrices with the condition that the number of qubits in the input and the output of the gate must be equal. So these are the various quantum gates that we have. Some of the quantum gates like Hadamard gate, T gate, C naught gate, Toffoli gate, Pauli jet gate, jet rotation gate, NOT gate. So they have every gate has their own purpose, and the number of qubits, if you observe, they take are limited in the number. So Toffoli gate is taking about 3 qubits as an input and process to provide certain operations. Quantum programs or the algorithms are the circuits that made by a combination of the quantum gates. The quantum algorithms work by applying quantum operations in the form of quantum gates on the qubits, like how the classical programs are working are based upon the circuits on the classical gates. Quantum program executes on the quantum processors, which we call it as a quantum program unit or processing unit. Quantum technology is still maturing computing technology. There are certain hurdles left to overcome in order to build fully scalable computers. We will list out certain building blocks. One is the realization of the quantum computers because of the noise, and one just example is that they are sensitive to the noise. As we have said, noise causes quantum system to decohere and lose its quantum properties, and there is a lot of room for progress in devising especially quantum error correction schemes as well as engineering advancements towards suppressing the noise effect. So what are the various applications? At this particular moment of time, people are trying to address certain building the algorithms for essentially solving optimization problems, sampling problems, and typically both are there in the machine learning. So trying to connect the machine learning also through quantum computing. So there are non-linear polynomial optimization problems with discrete variables. So let us see, the primary focus of quantum computing now is the optimization problems, where the goal is to find the best decision out of large number of possible decisions. So they are typically difficult to solve in the real world, and in almost every business operations, people identify a lot of optimization problems, and people are trying to build quantum algorithms for it. And the sampling problems, wherein which sampling is the technique of drawing values from a solution space that allow generalization about the distribution of the population. And classical computers are struggling to efficiently generate the random examples of certain phenomena that handles the particular these problems. However, if complex quantum states can be controlled, sampling these states can be done much more in an efficient manner, especially in the data mining and related problems. So machine learning is based on both sampling and optimization problems, and hence the ability to improve these techniques will lead to a better machine learning capability as an outcome. So people are trying to address optimization problems and sampling problems, and hence there are some attempts now to bring the quantum algorithms towards machine learning. These are the various sectors like financial services, healthcare, manufacturing, and resource optimization, media and technology. And this particular slide would give a better picture of what are the various applications or use cases of quantum computers in automotive, aeronautics, material science, finance, defense, energy, and all. Especially drug discovery is the one of the area where in which people are trying to explore the quantum computing. Now, if you observe the startups and all, the hardware focused startups and the software focused startup and both incumbent firms, we can identify there is a trend about from 2015 onwards. The startups are heavily investing or focusing on both hardware and software than the incumbent firms such as Google and even IBM and all that. That's one way good sign, and another way it is a sign that this is a technology that still there is a uncertainty about number one, maturity level and the time to maturity and the applications aspect. So that's the another reason probably there is a push from the startups than much push from the incumbent. So this slide gives a better picture about who is rapidly progressing in terms of incumbent companies. IBM is leading a lot than other companies in terms of North American incumbents, and in the Asia also NTT is leading than all other companies, especially in the startups. D-Wave, because of their huge investment in quantum annealers and then building the quantum computers with about 1,000 to 2,000 qubits, they are leading in the startup firms. So these are the four benefits of having a quantum computer. One is the superposed states, wherein which all possible states are available to perform the computations. That is one of the significant advantage. And another one is that the outcome is probabilistic in nature. Any given system can be observed. And entanglement is the one with which superposition and entangled qubits are the one enormous power. And wave particle duality, all these things are contributing to the quantum computing potentiality. There are various simulator platforms that are available for the everyone to explore, especially IBM Qiskit and Google Cirq and Microsoft QShark. And among that, IBM Qiskit and Google Cirq are dominating and people are using. Of course, there are other simulators, both the researchers and the industry, they are heavily dependent on using these simulator platforms to explore small qubits and quantum gates and all that. And gate-based quantum computers are available from IBM. People can look at research.ibm.com. Similarly, adiabatic quantum computers are supplied by D-Wave, and we can have a look at it, both these gate-based quantum computers and as well as adiabatic quantum computers. So as of now, Google has about 72 qubit quantum processor, and IBM has 53 qubit. There was about a discussion about Google achieving the quantum supremacy about a few months back, and TFR of India also has developed about 3 qubit quantum system. And there is about a beautiful resource from Quantum Algorithm Jew, which is listing about several quantum algorithms that one can look at these algorithms and see how they are working. So the major constraint is that the number of coefficients, especially when the number of basic states, the number of qubits are increasing, the number of coefficients required to describe the state of quantum computer increases exponentially. That is one of the challenge or constraint. Similarly, the second constraint is it is impossible to make a copy of the quantum system because of the non-cloning principle. Though it is a constraint, in one way it is a kind of a strength to the security related problems. Similarly, the third main constraint is because of the handling, the way the noise immunity to be achieved for handling the quantum operation. And there are several other bottlenecks or the risks, especially in having the quantum computer or realizing the quantum computers that need to be addressed is designing the quantum algorithms, that is for the given any problem. Similarly, how to handle the data inputs and give these inputs to the algorithms, or how to load this data to the quantum computers, or whether we can design error-free quantum computers or not, how to handle the noise towards at the quantum bits. So these are the various problems that needs to be addressed. Similarly, developing the new software stack. Recently, there was an article on IEEE Spectrum giving a complete architecture of quantum, the applications, data, then input to output, and then QPU, having entire software stack about that was a proposal given. Similarly, these are the issues that needs to be addressed before we get into a full-fledged quantum computer. And as of now, we have NISQ systems people are trying to explore, and in order to achieve that, we need to have, in order to have a logic qubits, more number of physical qubits are required. That is the major bottleneck with NISQ quantum computers. So these are the references. Those who are interested to look at some of the, of course, I have given it at appropriate places what are all the literature that is this one. In addition to that, there are interesting books recently coming up. Especially a primer on quantum computing is a simple and interesting to read, and also quantum computing and applied approach is also a simple book one can read, so that we can understand the complex terminology, concepts, right from coming from physics, math, the computer science, everything connected together. So I think these books are making the job easier in understanding. That's all I have now, and thank you very much to everybody for their patience.
Thank you, Dr. Aswani Kumar, for a wonderful presentation, giving an overview of quantum computing and explaining the features. So thank you very much. We have a few questions. First thing, can we use the conventional programming languages in quantum computing?
So people are actually trying to build, in order to build the algorithms, in order to write the programs. Of course, there are now libraries that are coming in, especially from Python. There is a support, but the point is that when we want to really build the quantum computers, as I've mentioned, the separate programming and the software stack need to be built in. But as of now, people are using C, C++, Java through the simulators, as I have listed. People are exploring it.
So, which means that this means that we require a totally different type of skill set, is it, for operating with the quantum computing?
Yes, with simulations, people are exploring with C, C++, Python. They are trying to simulate on the classical computer.
So when you simulate, does it mean that, basically it goes to the emulation mode. Does it mean that we will be compromising on the speed?
What is that?
No. See, when they simulate the quantum computing using conventional programming languages, so it is more or less that we are trying to emulate the functions, right?
Correct.
So does it mean that we will be compromising the speed of the quantum computing?
We have not achieved the true potential of quantum computing, but it's not that we truly achieved the speed of quantum computing. We are just trying to mimic the behavior of it.
So we are basically studying the performance and features and things like that, right? Trying to understand. Basically, it is okay. See, how the superposition gets speeded up if they are probabilistic in nature?
How the superposition?
Speed up calculation if they are probabilistic in nature.
So actually, it is like this, sir. When 2 qubits, as I have shown in one of the slides, especially when we are discussing about the wave function, they are in a superposition state, and when we measure only, the outcome comes. So as long as we have not measured, they are in the superposition state. Only when we measure, the outcome would come, and the outcome would be in the probabilistic nature. It depends upon the basis value, or else is the complex coefficient value that is chosen for that as a basis for that particular qubit. So if we observe the way what we have given for single qubit, A0 and 0 and plus A1 or for the basis state 1. So now the A0 is the complex coefficient. So that would determine the probabilistic outcome.
Okay. Can you briefly explain about the contributions of Indian researchers in quantum computing, and recently Government of India has also announced the quantum computing mission, right? Some funding has been allotted. Can you just brief what is it happening?
So I have I have read in the DST website about allotment of about 80 crore fund towards the DST initiative, Government of India initiative on quantum computing. I understand some of the the central government institutes such as one is TAFR heavily working on quantum computer, and I think they have realized about a 3-qubit quantum computer. But in addition to that, CDAC Mohali recently they have organized one faculty development program through AICT Atal program. Through that, I understand that they are also contributing heavily towards quantum computing, and in collaboration with some of the MNCs such as Atos and all that. So now things are accelerating. Only thing is this needs a kind of joint contribution in terms of computer science, physics, mathematicians coming together and working together. That is on developing the quantum algorithms per se. And in terms of applications, again, the computer scientists and disciplines such as biology, healthcare, they also should work together and developing new drugs. So I think there is a wide scope for that. Only thing is that people are not sure about how long it will take in order to achieve a truly built quantum computer, or else without noise-free quantum computers. So nobody is able to give precise answers, and hence people are a little cautious about what would be the timeline, whether it is another 10 years timeline or whether it is another 5 years timeline. But people want to move in this direction. And another side is that having application oriented towards only a subset of problems that classical computers are not able to solve. So that is another one way we can say as a challenge, or a kind of a bottleneck, or people are not aggressively moving towards it because it is able to solve only a few set of problems.
Okay.
Cost involved. Cost involved.
Okay. What type of storage technologies go together with quantum computers?
That, as I have mentioned in one of the slides, the people are trying to explore, I think, the solid state physics, and that part I think I have mentioned in one of the slides, sir. In details, I think the qubit realization, people are trying to explore the trapped ions, the semiconductors and all, but it is still, a lot of maturity has to come in these areas.
So which means that associated hardware with quantum computing are still under development, right? Okay. And,
the hardware is the main, this one, rather than the software.
Okay. How does quantum computing compare with biocomputing?
Biocomputing, can you a little bit elaborate, sir?
No. Biocomputing also it has got potential for future. That's what many are claiming. So is it easier to go with biocomputing rather than quantum computing, or how do they basically?
To be frank enough, I'm not precisely know about the biocomputing. I think if it is a cognitive computing, people are heavily pushing cognitive computing than quantum, especially in the book chapter. What I read about the drawbacks or the limitations of the von Neumann computer, the authors are trying to rather push the cognitive computing or cognitive technology than quantum in order to address the limitations of the von Neumann computers. The point is that the quantum is trying to, or people are trying to propose quantum as an alternate technology in order to address the von Neumann problems. But whereas the other researchers in the literature, I find that there are people pushing cognitive computing. The reason is that on the other side, especially the cognitive, it is mainly the software part of it rather than hardware. Now, hardware already we have. So I think cognitive is moving in that direction.
Okay, there are different types of metrics are being used for benchmarking quantum computers. I think people, they say that the more number of qubits are better. IBM comes with a new formula of quantum volume. Can you briefly explain how people are benchmarking quantum computers?
One of the metric is the fidelity and the number of qubits. But having NISQ computers, in order to realize the quantum computers or qubits, logical qubits, we need more number of in order, especially because of the noisy environments, we need more number of qubits in order to realize the qubits. So fidelity is one of the metric that people are trying to measure, and so one is fidelity, sir. Yes.
Okay. And what type of qualification one needs to sort of gain in order to get into quantum computing area? Or what are the courses maybe useful?
Yeah, the predominantly I have one or two Coursera courses I saw in the Coursera. If anybody wants to learn about quantum computing, there are one or two courses. But if somebody wants to dive into this area, the main thing is if you observe the core concepts, especially from the mathematics, the linear algebra principles, advanced linear algebra principles, coupled with the the tensors and the Hilbert spaces. That is on the mathematics part of it. And on the other side of computer science, I think if people are good at the Python and using the standard libraries, science aspects such as computer architecture and all that, I think people would be able to move forward. Especially even the non-computer science professionals especially from physics background, I think they are also contributing more towards realization of qubits. That also is there, and now in the last couple of years, we have certain books that have come, especially from Springer on quantum computing, which I thought that would be a good point for.
People to start with.
Yeah, learning point to start.
Okay. Can you give some briefing about the adoption of quantum computing around the globe? I said how far it is getting adopted, and there are people say that quantum computers are also available on cloud.
Correct. So the IBM as the IBM is providing their cloud computing through cloud computing through cloud platforms. They are giving the access to the IBM quantum cloud. Google Circ is giving, but of course I think there is some kind of a payment involved. But IBM is doing that. Anybody, students and professionals who wants to play with the quantum gates, IBM Qiskit is the best one to start and then do. And there are a lot of help manuals and tutorials available to play with it.
Okay, you are mentioning about the gate errors and noise in quantum computing. Are they detrimental for the processing speed or accuracy?
It is for accuracy.
So which means we can't be guaranteed about the accuracy of quantum computing results, is it?
Correct. That is why we need to have more number of quantum qubits, sir. At now, as of now.
Okay. And we have been hearing a lot about post-quantum cryptography. Can you briefly explain post-quantum cryptography, which is being talked about a lot of We read a lot about that.
So the one fundamental challenge the quantum computing is throwing at the current the computer science scientist is the ability to solve certain complex problems that the security is built upon, especially public key cryptography is built upon the non-tractability, or conventional computers are not able to solve certain mathematical problems, especially the prime factorization problem for a given large number. So the Shor algorithm, in fact, in order to delay Shor algorithm, we need about 10,000 qubits, more than 10,000 qubits. But whereas the current the current quantum computers that are built by the Google and the IBM are 50 and 50 or
71 or something.
70 and 100. So it takes a lot of time to move towards having the with the bits with such bits, but the quantum computers theoretically are having the ability to solve these problems. So that is the one of the major challenge that quantum computers are posing, and hence the scientists are trying to build quantum resistance algorithms. So that is what people call it as the post-quantum cryptography. And recently NIST has released note on that, and they have in fact invited certain proposals for post-quantum cryptographic algorithms, and there are some submissions to that. And similarly, another interesting problem that the of course post-quantum cryptography or the computers, the security professionals are working on the quantum key distribution, in the sense that in a typical key distribution problem of security, wherein which a symmetric key that need to be shared between the two nodes, how security need to be shared is, again, people use public key concept to share the secret key. So now with the Shor algorithm, the security of public key cryptography itself is in a threat, and hence people are trying to use the quantum cryptographic principles, especially to distribute the shared key. People are proposing quantum key distribution principles, and in fact there are some commercial applications also that have come, but I'm not sure whether they really implemented the quantum phenomena, because that is yet to be achieved. So but QKD is one of the interesting problem, quantum key distribution.
Okay, one last question. How is China progressing in quantum computing?
I think when comparing with India, like in all other disciplines, they're much ahead in terms of quantum computer. Recently, about I think about 2-3 months back, or 4-5 months back, I have looked at an article wherein which they established a channel, quantum channel between China and Austria, wherein which they are able to communicate between these two nodes, one in China and one node in Vienna, through quantum channel, in which the keys are shared through QKD principle. So in that way, they are able to show that they are able to demonstrate the QKD quantum key distribution phenomena. The quantum channels are established, and in that way they are leading than our country. That I think we need to. Like in all other, yes,
we have to take into account that.
Yes,
so,
yes.
Thank you, Dr. Aswani Kumar, for your wonderful presentation once again. On behalf of the organizing units, ACM, Computer Society of India, and IEEE Computer Society, we would like to thank you for your time and effort in presenting this wonderful webinar. And our thanks to ACM Distinguished Speakers Program for approving this talk under this ACM Distinguished Speakers Lecture Series. So thank you very much. And we really look forward to your continued support to our activities in future too.
Thank you very much, for inviting me, and thanks to everybody for their patience listening. I hope my talk is useful, and I am really amazed to see Professor Mohan sir's the continuous contribution in the field of computer science, his activeness and energy, and continuity and follow up and cross checking. And I'm observing Professor Mohan from about 13 years, and same enthusiasm. I have not seen any kind of decline with his age. I think he's more and more becoming young in the spirit. And thank you very much, sir.
Thank you. Thank you. Before we formally close it, I have few announcements regarding our future programs. On 27th, we have a program on social media analytics and NLP. On 31st, we have a program on DevOps and Kubernetes. On 3rd November, we have a program on mobile app development. So we have already sent invitations to our members and other groups. Please make it convenient to register and attend these programs. So with this, we'd like to close our session today. So thanks for your participation. And once again, thanks to Dr. Aswani Kumar for his excellent presentation. Thank you and good night. Okay, Akla, we can close the thing. Recording, we can stop.